Our first speaker is Ismael Mourifie from University of Toronto. He'll talk about generalized instrumental inequalities.
Thank you very much. Thank you for coming here. And thank you for including my paper during that amazing conference. I would like to really thank Frederic that has been organizing. I am a long-term visitor here so there are many different workshops that we had. And this one is an amazing one. And I would like a round of applause for Thomas. Thank you very much. I was very excited about this presentation because initially I started my bachelor in math and physics, and it was too difficult for me, and then I moved in stat. And stat was too difficult, and I moved in economics, right? And then I just came during that workshop, and then I saw yesterday a lot of things about physics. I said, oh my God, that's coming back to haunt myself, right? But you know, I think I have been working on causality, like in economics. I am from the economics department, and one of the important models that we have been working a lot in economics is this, you know, IV type of structure, this particular bag of structure, and it's something like very important in economics, particularly because many of the structure that we have seems to have this very simple structure, IV structure, that structure here, where this is for us, for example, the treatment, think about college education, and then has some impact on your earnings, for example. And the fact is you have a bunch of confounding that may affect your decision to go to the college, but may affect also your earnings. One of the examples could be, for example, the level of education of your parents. It may affect your level of education, but also the network of your parent may give you better wage. Better earnings and so on. So you have this confounding, but we want to extract what is the causal effect of Y, you know, from Y. So what we have usually, we use this IV type of structure where you're gonna say that there is a random variable, Z, that's gonna affect the treatment, but will not have any effect on the confounding. And we're gonna use this to try to extract what is the causal effect between D and Y. The question is, in economics, we come with random idea about what is the Z variable, right? And we are not in agreement about what is the good Z variable, right? So it's very important for us to try to have a good idea of if we could test the validity of that IV, of that instrument. One of the person, like just in the economics department, David Card, got the Nobel Prize this year. When he was trying to find an IV for the treatment, he used college education. He used like distance to college. He said that distance to college may be something that's going to affect your treatment, but it's not directly related to your earnings. And many people complain because if your parents are really smart, maybe they're going to live close to Berkeley here, and then you are close to the. So maybe you're going to have some confounding here. And then in economics, we do not have like this intuition of testing the IV because some of the first paper that was in the literature say that the IV is not testable. So you cannot really test if that structure is valid or not. It's more recently with all those work on Pearl inequality, you know, Bellman inequality, that now we start to dig a little bit into that literature. Right? So that's why I want to talk a little bit how to falsify this type of model. So this is going to be basically what I will try to discuss today, okay? And I saw a lot of interesting things yesterday, so I will try to relate my talk a little bit with what of the discussion that we saw yesterday. But as I told you, you know, I move away from physics because I am very bad in physics. So if I misinterpreted what you did yesterday is my fault, right? So what I will try to do, this is basically a bunch of like summary of what I want to do here. I want to derive a bound on the average causal effect, which is like what is the causal effect of the D over the Y. Because of this confounding, I cannot really uniquely recover that by one GDP. So it might have a bunch of distribution that can rationalize this. And then I want to know what is the lower bound and what is the upper bound of my effect. And the bound that I'm gonna derive, gonna try to generalize different paper that has been trying to achieve the same goal. Before us, there is like Jamie, there is Mensky in economics, there is Beck and Pearl. So there are many different approaches that has been used to derive similar bound. So what I will do here, why is like is a little bit new is because many of those structures use the case when the outcome is discrete, and all those variables are discrete in general. Not the latent one, we do not observe the latent one, but they impose discreteness over here. In economics, we are really interested to earnings, which is continuous. And this random variable also could be distance to college, which could be continuous. So the question is how to generalize those structure when you have Y and Z that is potentially continuous. If you think about the presentation of Eddie yesterday, and then these techniques of inflation, you could see that if as soon as you get into the continuous space, you're going to have a lot of possibility of inflation, right? So this is the type of structure that I want to get, right? How to get, in that very general framework and that we want to do. So in that framework, I will try to derive what I'm going to call this instrumental inequality. I will call generalized instrumental inequality, because you will see that the inequality that I'm going to derive going to contain the Pearl's inequalities. It's going to contain some of the inequalities that Thomas and co-author has been, and then the Bonnet one, and also it's going to contain the what you call the CHSH type of inequality, right? And now the question will be, you will see the inequality going to be a bit complex on how to test the validity, because I'm going to have a lot of inequality. So I will discuss a little bit about the complexity of that type of inequality. I think I spent 10 minutes to just say what I will do. Anyway, let's see what it works. So I will start with the potential outcome framework. So instead of looking at that DAG, one equivalent structure is to put in the potential outcome framework, where I'm going to call my outcome going to be Y, and the potential outcome going to be Y1 and Y0. So Y1 and Y0 are unobserved, and D is my treatment. So if I decide to go to the college, this is my earnings that I'm going to receive. If I decide not to go to college, this is my earnings that I'm going to receive, right? And what you receive, your earning is a mixture of those two types of components. Now, what I want is my random variable Y could be continuous, so it's a very general case. I'm going to have my treatment, I will fix to be binary just for simplicity, but I will allow my IV to be large dimension, to be continuous, right? Whatever you want, okay? So this is the structure that I have, and then I will impose some assumption, which is like my potential outcome here. The fact that I put what I call this exclusion restriction, say that there is no channel that move directly from the earnings to the, so here you see I have no channel here. So this is the exclusion restriction, right? So my Z does not have a direct effect on my Y. So this is what I put as exclusion restriction here. And the fact that I do not have any channel between Z and U is the fact that I'm imposing that independence assumption. So you could think my U here as just my potential outcome, YD, right? In the way of writing. So you could put just here, if you want, Y1, Y0, whatever as a potential outcome. Make sense to you? Good. So now the question to me is what I will call the average causal effect is going to be what's going to be my earnings if I decide to go to college minus my earnings if I decide not to go to college. What are my parameter of interest that I am really interested in. Good. So now let me show how I will bound this in the situation where my IV and my earnings are continuous, right? I will move from the discreteness that we have in some of the paper. So this is the density function of this potential outcome YD. Makes sense? Now, what I will do, I will use the independence because my IV is independent of the potential outcome YD. So you could make this conditional. You have the equality here. Make sense to us? Okay. Now, what I will do a base decomposition. So my potential outcome YD, I will decompose as if I am getting treated, this is equal to do, or if I am not getting treated, if I am not going to college. This is just simple base decomposition. But this one is density, right? Because the density is, we have the positivity of the density. So this is going to be bigger than 0. So this left-hand side is going to always be bigger than this side. But this is going to be true for all Z. Make sense to you? So if it's going to be true for all Z, I can then take the supremum over Z. and making the intuition about what I saw yesterday, when you perturb a little bit the Alice and the Bob things, this is the way that you could see the interpretation here. So I move the Z, like in the different value, but whatever I move that particular Z, it should not dominate this because of the potential independence assumption that I am putting here. So the intuition is, because this one has only one channel through D, moving this too much should not affect this that much, because all this effect has to be translated by this particular D, right? So I'm gonna have all this density should dominate this one every time. So what I will do, I could integrate over that density if I am taking any Borel set, any A belongs to the Borel set of Y. So let me take that integration. So what I will do, if I integrate this over A, I am getting the probability of YD belong to A. Make sense? And I could make the integral here over the same density. So what I will get a bound, a lower bound for this probability distribution. And I do the same thing for A complementarity, and I am getting an upper bound for my probability distribution. Does that make sense to you? So this allows me to bound the conditional probability of going to the particular treatment Z. Makes sense to you? But if my model is right, the lower bound has to be always lower than the upper bound. And this is observable from the data. And then the question is that always true in the data? This may not always be true in the data. So if my lower bound in the data is bigger than my upper bound, that means that my model is wrong. And something is wrong in my structure that I am putting here. Does that make sense to you? So this is a simple argument that I will do. I will say, okay, if this lower bound is lower than this and lower than this, I need always to have this one should be always lower than this one. If you rearrange this, you get that inequality. And this is exactly what people call the Pearl inequality when you write in the discrete case. So if you say the outcome is discrete, this is going to be a probability. You say Z is discrete, you're going to have the supermem over Z here, and then you get that inequality, which is coming from the Bell inequality. And this is the Bell inequality. Does that make sense so far? Now the question is, we know well this Pearl inequality, but beyond the Pearl inequality, there is other inequality like the Bonnet inequality or like the CHSH inequality. So let me try to see how I can get those type of inequality using my little algebra that I have here, right? So before, if you remember, when I put the independence assumption, I put the independence assumption only on the single potential outcome, not jointly. Right? Now what I will do, I will put the independence for the joint potential outcome. The fact that I will put for the joint potential outcome gonna give me a lot more power. And I interpret this as the outcome of this Alice and Bob type of situation that we're gonna have, right? And then I have the full independence here, and then I still have this exclusion. Okay, in some of the work, for example, Thomas liked to call this the type of crossword assumption, right? Because this is a potential outcome if you are not graduating, if the potential outcome if you are graduating is like two different dimensions where you are, right? My point is this crossword assumption gonna give you additional power, including particularly the Bonnet one and the CHSH type of inequality. So how I get that? Let me take Y, which is the support of the outcome. And because my outcome could be continuous, I will take any partition of Y, of my support of the outcome, right? So let me take a partition that I'm gonna call a partition like BL, so a partition of the Bob partition. So like I'm discussing any, perturb that I can have over Bob. And then I will take a partition also over Alice, any perturb way that I could have like over the, Alice type of outcome. So what I will do now, I will write down the joint distribution between Y0 and Y1. Okay, you all agree. Now, what is interesting to me is, again, I am relating to this inflation, that I saw yesterday, right? When you change the model a little bit, because I'm gonna take all type of potential partition that I could perturb for the Alice and for the Bob, and I have this joint distribution. But because my joint distribution is independent of Z, I could put this one is independent, is conditioning to Z. That makes sense? You are good? So now because I am putting this, and because I have the potential outcome structure, which you remember as this. Minus D. What's going to happen is every time that I am taking the joint distribution, I start by Y0. Y0 belongs to A, and Y1 belongs to B. That I am given over Z. What I will do, I could do the same base decomposition. So I will put a D everywhere. So it's going to have Y0, Y1, tac, tac, D is equal to 0, given Z. So we are very slopey. And Y0, Y1, D is equal to 1, given Z. Does that make sense? Just base decomposition. Now, this is a joint distribution, but the joint distribution is going to be dominated by the marginal if I remove this. And this joint distribution is going to be dominated by the marginal if I remove this. So this is what I am putting here. The hyperbound. Right? Now what I do, because this has to be true for all Z, I can take the infimum over Z. And I get that joint distribution has to be lower to this one. So why is interesting and why is sometimes I got the feeling that it was related to what is at Mirjam, the pronunciation, my pronunciation is very bad about your name when you were doing your presentation yesterday, because she has this joint distribution and then she's look at the level of dependence that she could have between those, if you could allow perfect correlation or not perfect correlation, right? If you look at this joint distribution, the well-known bound for the joint distribution is the Fréchet hyperbound, right? If you are familiar with that, not really. So when you have a joint distribution, like probability of Y1 belong to A and Y0 belong to B, whatever, this is gonna be always lower than mean of this probability of YY belong to A and probability of Y0 belong to B. This is what people call the Fréchet hyperbound. It corresponds to the case where there's a perfect correlation between those two random variables. But here, you cannot allow necessarily all perfect correlation between those two because there is this bound that is observable. You see what I mean? So if this one, for example, is lower than the product of those two, you cannot allow strict perfect correlation between those two types of random variables. Okay, so this restriction is gonna restrict my joint distribution that I'm gonna have here, and then I'm gonna have like this hyperbound. So what I will do the same thing. I am integrated over this marginal to get this one. Okay, I forgot something here. Okay, I messed up something here. So what I do, okay, forget about that, right? Look at this one. And now if I want just to get that marginal, what I will do, I'm making a summation over the partition of the Bob here. Partition. So I will always get this one gonna be always lower than the summation over the second partition over this here. And what I will do, I could do the same thing also for A complementary and do the same thing and get the lower bound of this and then the hyperbound of this. So from the joint distribution, from the restriction of the joint distribution, I am able to bound the marginal. And that bound are different from the previous bound that I showed to you. You remember about that I have like in the previous. So here I get information from the joint distribution. So now how am I gonna make use of all those two assumptions, right? I know that is a little bit messy. My notation is a little bit messy, but I have two types of bound that I can construct. I can construct the bound on the marginal. This is what I show you was equivalent to the Pearl type of inequality. And then I have another type of bound that I construct that is coming from the joint distribution. Right? But this is the same quantity that I have in the middle. Make sense to you? If my model is true, that lower bound has to be lower than this upper bound. This is what we have, and this is give the Pearl inequality. But if my model is true also, this lower bound has to be lower than this one too. If you do the math, this is gonna give the Bonnet inequality, and it's gonna give the CH-SH. I am French, so that's sometimes I am say that is C. The CH, SH type of of inequality. That makes sense to you? So this is the way that I am deriving that inequality, like from scratch. And this is true for any continuum Z or continuous Y that you're gonna have. So you have like a bit generalized. So what I'm gonna call generalized instrumental inequality, I'm gonna say that the maximum of that lower bound has to be lower than the maximum of this upper bound. So this is gonna happen. And if you do this, you get what I am calling the generalized instrumental inequality. Does that make sense to you? That I can get for any value of Z and any value of Y in my distribution. Now, where things start to be tricky is if you look at very well, the bound that I have here depends on the partition that I decide to have. So my instrumental inequality is gonna really depend on the partition that I decide from the beginning. So if I want to get the most information to test the validity of my model, I have to go over all the potential partition. If Y is binary, you get everything which is the Beck and Pearl type of inequality, because everything is one binary, you get all the partition very simply. When Y start to be continuous, start to be tricky. If I have a methodology to do that, I cannot tell you, right? It's something that I have been discussing like with Richard, like since I have been here. So if it is discrete, it's good because Thomas also have all this linear programming that you could do. Then you could put like in the linear programming, if your Y is discrete, your Z is discrete, you could do that well. But when it's continuous, it's a little bit complicated to do the game. So it's something that I did not really, we did not really entirely show like how it, what we prove with one of my co-authors here is if Y is binary, but the Z is continuous, what I show you as a generalized instrumental inequality is a sharp one. You get all the information that we have. And how we show that? We look at in the bound that we have, we show that any distribution that falls down within that bound could rationalize my data in the same way of the inflation technique that you have been discussing yesterday. So I basically, for any distribution that falls within my bound, I construct a model that exactly delivers the same observable outcome in the model. But we did that in the binary outcome case and continuous Z, using some things from the optimal transport type of technique that we do to that. But when outcomes start to be continuous, I do not have any proof for that yet. We do not have any proof for that. And then it's something that we're still thinking about that. And then, yes, how I'm doing in terms of time, very bad, I guess. So I have 40 minutes, right? So if I have 40 minutes, I have 15 minutes more. So that's super, that's fantastic. Okay, good. So what is difficult is this following things. Assuming that Y is continuous, and then I am fixing a particular partition and I am not taking all the partition, all the potential partition. I'm gonna get a set of inequality. If they are violated, I say that my model is wrong. But if they are not violated, can I say anything reasonable? Again, I was discussing with Eli yesterday, and I talked about the case when the outcome is continuous. And then he said that there's an inflation technique, there's a way to do something using the moment, right? So you have like a moment characterization. Instead of taking all the distribution, you could use the moment and do that. But let's think that you do that for a minute. In that case, if you do that, you may not try to cover some of the distribution that does not necessarily, equal with that moment. In that case, even if your inequality or your inflation test failed, how should we interpret your result? Is that your model valid? Could you use it or not? Does that make sense to you? In economics, we have that issue because in many of our applications, Y is continuous. And since we have this Pearl inequality and some of this paper, many of our colleagues start to use the inequality that we derive, and they discretize the outcome. So even if the outcome is continuous, they discretize binary outcome, and they do our test. And when it's not rejected, they say, oh, my IV is good. And then they apply this structure. And this was very disturbing to me, because in the sense when we wrote the paper, was not my, I know that I did not solve the problem. We did not solve the problem entirely. And then it was I saw all this referee report, and I have to say, I like that people use this test, but I am not really in agreement. So I was trying to understand, we were trying to understand with my colleague here, so how we could interpret if we do not use all the information, but we use only some part of the information. Is that something that we could get something relevant to say to people, or policy relevant? So let me show you a simple design that we did that. That's gonna give a very bad answer to this question, and very big concern for me and for my co-author. Is we're gonna consider a very simple design where the outcome is discrete, is binary, just the indicator. We're gonna have the treatment also is binary, and then we're gonna have the Z, which is multi-value, which is take 100. We're gonna allow the exclusion, but we're gonna permit some potential dependence between Z and U. So we're gonna allow a channel here, a correlation here. So because we allow this correlation, our first IV model is wrong, right? In the simulation, in the data. So what I will do, I will construct the bond of Minsky and Robbins using only the Pearl inequality, not the CH, SH, and not the Bonnet inequality, and not our generalized inequality, just the Pearl inequality that has been derived in Minsky and Robbins' paper, to get what is the bond on the potential. So it's gonna be the average here of Y1 if you decide to go to college, and Y0 if you're not. So my set of parameters is theta 0, theta 1. This is my set of parameters. So when I apply those bonds, this is the interval that I am getting, okay? So what that really means actually, if you look at what's gonna happen, I should have used beta. So think about here is theta 1, and here is theta 0, okay? So the type of interval that I am getting here is, yeah, I'm very bad. So let's do that. So think about something. I say something like that. Okay, I do that. And this is what I am using, the type of, Jamie or Minsky type of bond. So I do not use all the information, just the Pearl inequality. And here I do the same thing where I use the CH and the Bonnet, but not this one. So I'm not using the all informative bond, I use a part of the bond. What I am getting a different set. And that set is gonna be, do not look at the number, but what's gonna happen is I'm gonna have something like that. See what I mean? So if I use a part of the all information, I am getting that information. If I am using another part, I am getting that information. But assume that I am a policymaker and I want the result to say if I have to bring my child to school or not. And you come and you ping the bond from like the Pearl inequality, and you tell me, oh, the parameter theta should be here. And the second one came, taken over, and you say, oh, the parameter should be here. And the intercept of those two are empty. You see what I mean? So if I was doing all the inequality together, I will realize that my model is wrong and I will not use the IV. But because I am doing separately, I am getting some bonds, and I tend to interpret that bond as a good causal effect. Does that make sense to you? So using a subgroup of inequality, which does not deliver the whole information, could be very problematic in terms of interpretation. because I don't know how people should interpret that. Did that make sense to you? So here, if I am taking the identify set based on the Robbie and Minsky, and I intercept with the identify set using what I call the what Thomas called the crossword, I took from his paper anyway. And then you take the intercept and then you get the empty set. Does that make sense to you? So how to solve that problem, I don't know. I have just some intuition that I will try to tell you, but I do not have like a complete way to solve that problem, right? Because the warning is, it's better as soon as you have a dark type of model that you want to test, it's better to leverage all the potential restriction in that model. If you use only a part of the restriction, it could be very problematic if you decide to make a recommendation based on this part of this, okay? So this is basically what I am trying to do. This question of finding this, the most informative set of inequality, this is what in economics we call sharpness. Right? And when the model is potentially wrong, we call that misspecification. Right? So what I will try to do here, I will try in the very simple case of binary outcome and binary treatment, I will try to give you one idea of how I think we could solve this type of problem. Right? So what I will do is intuitively, my intuition is going to be the following. I have this one, and I know that my model here is wrong. It's not a good model. Now, the way that it's wrong is because it's violated either the Pearl inequality, either the CH-SH inequality, or the Bonnet inequality. Now, my question is, I want to learn from the violation something, because the violation is giving me some information that I have been imposing here in that model. So what I will do, I have two types of restriction that I did here in that model. I cross that arrow, and I also say that there is no arrow here, right? So let me try, depending on the violation that I have, let me try to relax some of the arrows. So try to generalize a little bit my DAG. What I will do, I will put a potential arrow here. That's why now my model gonna have that structure. Because now my Y is gonna depend of if I get assigned to a particular school, and also if I am my distance from that school. So there's gonna be Y1. So my potential outcome gonna have this particular structure. Okay. The second thing now is, before I was imposing that my potential outcome was not dependent on Z, so I was killing this one. Right? Now I want to introduce this one, but how I will introduce this? I could introduce in many different ways, right? If I want to get rid of that assumption, I could do in a different way. Economically, sometimes we have intuition. We're gonna say that your parent education, for example, is not a good IV, or your distance to college is not necessarily a good IV, but if you are close to college, it will not hurt necessarily your earnings. Does that make sense? So I can give some kind of shape restriction about the direction where the IV could go. It makes sense to you? So here I will assume, oh, okay, my IV is not a good one because he has a direct effect, but my direct effect could be positive in general. I am willing to assume this. So I'm gonna put the arrow here and put a sign plus, just to say that it is positive. Make sense to you? So this is gonna be my first assumption. And what I will do a second one for the different assumption, if it's the other direction. So I will lay out all the potential relaxation that I may have from this one. So another possibility is to do this, is to take another arrow and put minus. Okay. So what I will do, for each of those small pieces, first I will start here and I write down the testable implication for that model. If it is wrong, I will cross this, I will look at this. You see what I mean? So I will basically do slightly by slightly, depending on the way that I have a rejection, to try to see if I can relax the model. And my intuition is to find the minimum level of relaxation that's gonna allow me to not reject the model. Does that make sense? And you could do this in the discrete case again, because it's very simple to say, okay, let this binary in the continuous. I don't know how to do it, but let's think in a very discrete case how I can do this type of scenario. So what I will do, my initial assumption, which is the IV model, is assuming that all are right. Because if you say that this is bigger and this is lower, if you put those together, you have equality, right? So the same thing here. So if I am put all the assumptions together, this is my usual IV model. So what I will do, I will look at what is the identified my bound if I just remove this. And what is my bound if I just remove this? And I will look at all the possibilities. Does that make sense to you? If I do this, this is exactly what's gonna happen. This is in the discrete. What I have to say is, in the discrete case, all the inequality collapse only to the Pearl inequality. In the binary, so in the binary Z, binary Y, and binary D, there is no CH, SH assumption restriction. There is no Bonnet restriction. We do not have more. So all the restrictions that I'm gonna be the Pearl inequalities that I'm gonna have here. So what I could easily show is, if the first inequality of Pearl is violated, it means that my assumption A2 is violated. And A2, if you go back here, is the case when Y10 is bigger than Y1. So this one should be negative. So this arrow should be negative. So I could relate each of the violation to each of the potential assumptions that I have. As soon as I do that, I could basically write down what I'm gonna call the robust bound, because the new bound that I'm gonna show will never be empty. Why it never be empty? Because if my model is wrong, I'm gonna relax it a little bit until I get no violation of my model. That makes sense? So this is the way that, this is what we call the identified set, is the bound over my whole model. So if this is the bound of my whole parameter, if all the inequality hold, then this is gonna be the usual back and Pearl type of bound. If one of the inequality holds, I relax the model and I construct the bound for this one. And this is gonna be corresponding to the case when I have just plus. You see what I mean? And the same thing for when I have minus, and so the same thing like that, okay? So if you do that structure, this set will never be empty, right? In that case, and what you could say to the policymaker, you could say, okay, if you're in that situation, do the estimation of this one. If all your Pearl inequality are valid, okay, you are okay. If one is violated, actually, there is a new DAG that you have to think about, is that DAG where this is plus, right? Or this is a DAG where this is minus. You see what I mean? So in this sample case, it looks very simple and easy to do. But when Z starts to be continuous and Y to be continuous, you can imagine all the potential scenario that we could have, right? So my direction that I want to take is to look at in the very discrete case to see what we could do first by using probably all this linear programming type of approach. But I do not have a completely general result for the continuous case and then for the continuous Y and the continuous Z. Does that make sense? So this is the end for me. Thank you very much.
Thank you. So just to go back to the logic that you had in this last step. So essentially you're making these, so I can see, supposing Z's randomized. So this assumption is kind of not, it's not in question. And then you're essentially allowing for direct effects that are Z is affecting Y not through D. So just so I understand, the inequality that you're seeing is that's violated. So sort of establishes that there is an effect there, but it is at the population level, right? Whereas the assumption that you're putting in is at the individual level. So I just wanted to ask about it.
This is a very good question. So in the two things, in the very binary case, I could do the same scenario if instead of imposing, the assumption that I'm imposing here, was a little bit stronger than what I needed, because I could have put here expectation of y1 bigger than y10, and then you could get the same result. I think this is what I should do to make a little bit more regarding your claim, but it's still valid as soon as we have this. The question is that putting the assumption at this individual level versus the aggregate level, putting more restriction than putting at the aggregate level? I don't think so in the binary case. But as soon as we move from the binary case, I am not certain. And that will be the case.
Just one other follow-up question. So in the setting where Z's an instrument with many levels, I mean, so there is this problem that people may go hunting basically, and they try to find two levels where things aren't violated. In fact, I think in the example that Pearl gives in his book,
yes,
compliance D is dichotomized, and he sort of checked through different places where he could dichotomize D, and it looks like it looks like the cutoff may have been selected to just make sure that the IV inequalities weren't violated, because they're very nearly violated.
Yes.
I don't know if that's the case.
Yes, actually, in economics, we do that quite a lot. in economics, in many papers in economics, they do that quite a lot, because what they do, and that's why I think this question of discretization is a very important question that we need to solve. Because what they do, people are smart, right? They give you the data only the way that the referee wants to see. So they see the distance to college is something that could be continuous. And then you're going to see in some paper, they will say, oh, let's take a binary variable, if there's a college in your state or not. But because they try the distance and they realize that it does not work well, and then they discretize. And when they do, okay, maybe a college in your city, when it does not work, they say, a college in your county. When it does not work, you see that in many economics papers, right? This and this and this. And then people basically disaggregate or aggregate at the particular level just because they are fishing a particular identification and a particular level to avoid the violation of this. And this is a very big concern, right? In that way, because it could get to this type of like policy recommendation that I was very discordant type of policy recommendation that we're gonna have. And that's why I think is an important problem that we need to solve to avoid all this fishing for for identification, as I can see.
I think Thomas may have inadvertently answered my question in passing, but I was wondering, in the story that you told in the binary case, how you settled on a violation of the exclusion restriction and not that Z was confounded. But I think you're just assuming subject matter knowledge that Z is randomized.
This is a very good point. Okay, there are two things that I can say to your answer. I can try to say to answer that question. The first thing is, assume even if there is indeed a correlation here, but I am decided to relax that path, the set that I will show you will never be empty. So it will never detect that there is a potential violation here. So relaxing that path completely gives a situation where the IV is no longer testable. Now, what you could do is, okay, if you are in the scenario like in statistics, you can say, oh, Z is purely randomized. Like we use one particular IV in economics is the month where you are born, right? Because it's gonna determine when you're gonna enter in college or not. This type of thing, if you think they are purely randomized, you can say, okay, maybe let's maintain this one and not this one. But it might be a situation where I can do the analogous of this. I can cross this and just allow this. But if I do this, this model will never also be rejected, right? So it's going to be really depend. Now I am thinking about it. I am like a Bayesian person. So depending on the prior that you have on the structure, I think you take one particular direction to try to implement in the model. We do that a lot in economics, but we do not like to say that we are Bayesian. Okay.
assume 1040, right?